All right, this is my video introducing Chapter 6. Now, Chapter 6 is about radicals, and well, you have a lot of history with radicals. You've been dealing with them since you probably first picked up a calculator. Um, what I like to say about this chapter, Chapter 6, is it is no one's least favorite chapter. There are a lot of chapters people don't like, but I don't think anybody hates Chapter 6. It's just one of those chapters that, I don't know, you have some familiarity with the topic and you've seen some of this before. In fact, we've actually previewed a little bit of this. And speaking of that, I want to emphasize this thing that I had showed you before, Hentschel's 5 levels of understanding a function. I don't know if I did it, but I think I said I was going to put it on my syllabus because it's such a common thing I go to. But basically what it says, and why I'm bringing it up now, is it's the 5 ways of understanding a function. Numerically, domain and range, the graph, manipulate, simplify, or rewrite. That's a big one in well, any function, but certainly in radicals. And then this idea of freeing the argument, which this one we've actually already done. And I don't want to get into it on this handout, on this lesson, but what I mean by freeing the argument, if I have something like this, I have to understand this function so well that I know how to get rid of the radical. And the way we get rid of the radical, of course, is squaring both sides. And that's the art, I suppose, of freeing the argument. We've canceled square root. And you have to understand square root fairly well to follow along with all of that. In other words, if you didn't really understand that square root had something to do with squaring, and they, well, cancel each other, which is how we free the argument, then you wouldn't understand this process. So yeah, square root and squaring are, we call them inverse operations, and we'll, we know to take advantage of that. And like I said, we've already talked about this in a previous, in homework 1, or homework 0, I guess it was in this class. All right, but how about all the other stuff that has to do with radicals? So there certainly is more. You can even tell here, domain and range, graph. I'm not going to get into all of those things, but really it's this one right here that I want to talk about, and that is simplifying. Now, simplifying covers so many sections in the book. The book doesn't just use my outline here and follow it one step at a time. They kind of go back and forth and talk about simplifying in several different sections. And I'll explain why. All right, so here are the 3 rules, and there really are only 3, for what we call simplified radical form. Now, by the way, this function's unique. Radicals, most functions do not have a simplified form. If you looked on your calculator, you'd see buttons like sine, cosine. We've already talked about logarithm. All of these functions, none of them really have a simplified form, but radicals do. And so again, it's unique to some functions, which is why I can't just use one word when I talk about dealing with functions. With other functions, we manipulate them, but there's no specific goal in terms of simplifying like there is with radicals. So it's just one of those times where what you're supposed to do, and it is to follow these three ideas here. So sometimes this is written a little more globally to talk about more than square roots, but it gets kind of muddy when, or I don't know, detailed if you try to talk about every radical, like higher powers. So I'm just talking about square roots here. No hidden perfect square factor under the radical. So no hidden perfect square factor under a square root, because I'm talking about squares. And I listed some perfect square factors. Like 4 is a perfect square, 9 is a perfect square, 16, 25, 36, 49, etc. And you can see where a numerical understanding comes in, because if you don't understand square roots, you wouldn't understand that those are perfect squares. All right. And then here's why I was saying the book takes its time to cover this whole topic, because this next one, no fraction under the radical, is talking about fractions, and the book doesn't mention fractions until later in the discussion. So early in the first half of the book, the author teaches us about number 1, and in the second half, these two have to do with fractions, so the author doesn't really bring those up until later. And what are they? So no fraction under the radical, and no radical in the denominator of a fraction. So these are our rules, and let's go through them. All right, so I have some examples already wrote out here. I haven't done them, but I wrote them out. All right, so I'm going to do this one, because I think this one's probably the only obvious one right here, 160. So I like to say it this way. Think of these numbers as your favorite numbers. Your favorite number is 4. Your favorite number is 9, 16. And 16 is obviously a factor of 160. In other words, I could write 160 as 16 times 10. And one of the things I want to think about when I do this is, did I accomplish my mission? Before I kind of continue here, did I accomplish my mission? My mission is, well, I haven't finished the problem yet. My mission is to finish the problem with a number here outside of the radical, and the only surviving radical should have what property? Yeah, it should have no perfect square factor under the radical. So factors of 10 are 2 and 5. There is no perfect square factor under the radical, so I have accomplished my mission. Now, I say that because it's almost comical how students misinterpret the rule, no hidden perfect square factor under the radical, with the implementation when you're doing this problem. So I'll give you an example. On this one, number 72, or problem, square root of 72, I've seen a lot of students, I don't know, getting just determined to factor it like this, because they see a 9 and they're just all excited. Look, I wrote a 9, and that is 3 square root of 8. All right. The motions I just went through to do that problem might feel kind of right, but the mission was not accomplished. The whole purpose of doing this was to make sure I had no perfect square factor. Now I say hidden. What's the hidden perfect square in 8? Or hidden, perfect square factor in 8. 8 has several factors, 2, 4, and 8, but it has a 4 in it. So there's absolutely no reason to entertain this step right here. 9 square root of 8? 8 is just as bad as 72. It has a perfect square factor in it. So there is a fix, but it certainly isn't to do the problem the way I just did it. All right. So yes, I want to factor 72. Yes, I want a perfect square under the first radical, but I don't just want anything like an 8 under the second radical. I want something that has no perfect square factor. So hopefully you see it. I'm going to factor 72 as 36 times 2. And if you wonder how were you supposed to think of 36, this is one of those things I mentioned the first day of class. is that to succeed in algebra, you need to be a master of this big times small. And, just noticing that's even, back to this, this is one of your favorite numbers. So you're looking for it for that reason. Yeah, you just got to be able to recognize this. All right, so that is 6 square root of 2, and mission accomplished. There is no perfect square under the radical. All right, 80. What is the... I said there's an easy fix. Okay. What is the hidden perfect square? There's actually 2 hidden perfect squares in 80. There's 4 and there's 16. In other words, 80 is 4 times 20, but 20 is no good. Let me write that down so you can see. If I wrote 4 times 20, I hope right away you would kind of feel uncomfortable with that 20 being there, because 20 is, well, it has a 4 in it. So I could also write it as 16. And so here's the easy fix. The easy fix is, if you can factor a number in more than one way, where you have a perfect square followed by another number, pick the largest. Pick the largest perfect square factor. And if you pick the largest perfect square factor, then the mission will be accomplished. So I don't want to say that's the rule. The rule we're following is this one here, but to get the best outcome, pick the largest one. All right, so I did that, and I'm going to get 4 times the square root of 5. So all of these are kind of what simplified radical form will look like. You may or may not have the number here, but you certainly will not have a hidden perfect square factor underneath the radical. All right, so that was just applying rule number 1. Rule number 2, actually, this one looks like it's rule number 3. So rule number 3 is no radical in the denominator. So I have this 3 square root of 5. And you know what I'm going to do? I'm going to multiply it by square root of 5 over 5. What that's going to accomplish is it's going to give me this pair. Square root of 5 next to another square root of 5. And that's something that, we could go through the long process of kind of reversing this multiplication process I did here. In other words, I could think of that as a square root of 5 times the square root of 5, which is a square root of 25. But when you see 2 of them like that, square root of 5, square root of 5, the answer is 5. Look at what I have even before I write the rest of this problem. I originally had a radical in the denominator, now I don't. So again, mission accomplished, no radical in the denominator. That is considered simplified radical form. This one is not okay. Yeah, because rule number 2, no radical, no fraction under the radical. Well, the way we handle that, and there are certain rules, by the way, all these rules I'm doing with the 1 square root becomes 2 square roots right here. That has to do with manipulating, right? Not every function works this way, but radicals work this way, where you can take, it's usually written this way, square root of a over b, and write it as the square root of a over the square root of b. Actually, it's the distributive property, and the thing I'm distributing is the radical. So I can distribute the radical in this situation. All right. Well, I don't know if you see it, but we're done with this problem. Right? Because 9 was already a perfect square. I didn't have to do that little thing that I did with this one, multiply it the top and bottom. I just took the square root of 9, got 3, it meets all the requirements. All right, now this next one requires some understanding of algebra, but it's algebra we've covered. So I am going to multiply the top and bottom by, I'm going to put it this way, by whatever it takes to get rid of that radical. And what is that? Well, it has a name called the conjugate. And the conjugate of something like this is when you have, we'll call it A minus B. A minus B, the conjugate is A plus B. So 5 minus rad 3, the conjugate is 5 plus rad 3. All right, why would I multiply top and bottom by the conjugate? It's going to give me on the bottom difference of squares. And I said there's some algebra behind this. If I have A times B times A minus B, I'm talking A squared minus B squared. I'll fix that. Minus B squared. So if A is 5 and B is rad 3, I'm going to have 5 squared minus the square root of 3 squared. So it's just a matter of working this out. I will say I am doing something here. I left the numerator factored because we've experienced chapter 5, or hopefully you've experienced chapter 5 by the time you're here. Having it factored allows you to cancel. In other words, that 6 is being multiplied by everything else on the line. The only thing left on the line is this, the parentheses. But since that 6 is being multiplied by everything else on the line, I could cancel. If I had chosen to multiply this out and add 30 plus 6 rad 3 over 22, you know what I would have to do? I just would have had to gone ahead and factor, because I can't cancel here. For example, I can't cancel that 30 with that 22 because that 30 is not multiplied by everything else on the line, right? So this wasn't even something I wanted to do, to multiply it out. No, I wanted it factored, so I left it factored. All right, but I'm going to clean that up here. Let's see, divide that by 2, I get 3, 11. In other words, I don't need it anymore. I could, now is a good time to go ahead and distribute that 3. So if I distribute a 3, we get 15 plus 3 rad 3 over 11. And this is simplified radical form because it meets all the requirements. All right. So I hope you understand something. It's almost hard to say where we were on this function. No, I mean, on my outline anyhow, we were simplifying. But in order to simplify, we had to manipulate. But I want to point out that everything I did here did involve a very strong relationship or understanding with numbers. In other words, you had to know, to find the hidden, you have to be good enough to look at this 80 and know what you're looking for, and to find the hidden perfect square factor of 16 in 80. So that's a very numerical thing. So understanding a function numerically is just very important. That's why I call this the introduction to the idea of radicals. Understand radicals numerically, and some of what we do, or at least the steps that you're going to see afterwards, will make a little bit more sense. All right, so that's my introduction to radicals, simplified radical form. I have a few more to share with you on more specific topics, but this is kind of a more general idea. All right, see you in the next video.